just check. So we'll start then really at the starting point of this presentation. We're looking particularly at the material science basis of product development. And the material science tetrahedron is something that was introduced coming up to about 10, 12 years ago now, looking at trying to establish the principles of how we link the measurement of input material properties through manufacturing parameters to the product performance. So there's quite an established pathway now of establishing what critical material attributes lead to the establishment of product performance, and then also modeling how processing parameters, whether it's blending speeds, filling rates, etc., also influence the product performance. And really at this stage, we've come around to establishing certain critical quality attributes to understand how these critical material attributes and the critical process parameters lead to and control the product performance. And if we think really around the structure of the product or these critical quality attributes, we can establish really three of these. And the first, of course, we have to have the correct chemical identity of the components in the product. At Q2 level, we need to have the correct concentration and composition. So not only do we need to have the right chemicals, we need to have the right concentrations. And then Q3 really establishes a structural element, which is to say that the product should have the same non-equilibrium state related to the arrangement of matter within that product. So really over the years, there's been significant efforts into establishing what these critical material attributes are. There's been a lot of work into looking at the critical process parameters, and then also measuring variety of metrics of performance and trying to relate those back through design of experiments approach. But really one of these aspects that has remained relatively difficult to explore, particularly in the case of inhalation powders, has been this structural component. So if we think then about what quality attributes might be suitable for identifying this Q3 structure, well, obviously the post-aerosolized formulation is really, really key for this, because that's the aerosol which gets inhaled into the lungs by the patient. And it's the properties of this aerosol which are, of course, key. So there's been a vast amount of work undertaken in the last 5 to 10 years, really looking at these post-aerosol formulations. And the typical approach that's used, of course, is cascade impaction. So we need to understand the particle size distribution and the chemical species of those aerosol particles. And that's a relatively well-established process using cascade impaction to work up the chemical dose to deposition and the particle size distribution. There is a limitation to that, which is that cascade impaction provides really limited information about the composition of mixed agglomerates. We know the particular dose of a drug that's landed on a specific stage of the NGI, but trying to identify whether we have mixed agglomerates present has been relatively difficult. And in this space, optical microscopy really has recently been upgraded using Raman microscopy approaches to try and provide chemical speciation of those powders that have been dispersed. So we can understand that in a little bit more detail. And in more recent years, of course, there's also been the Q3 structural analysis using dissolution assessment that's been undertaken by the colleagues down in Bath, and Rob Price and Nanopharm were originally members of this consortium in the early years, and looking at using dissolution testing to try and understand how structure of the aerosol particles that are emitted as the aerosol are also key. But if we look at this, there is, of course, the aspects that we have a pre-aerosolized formulation. And this pre-aerosolized formulation is really where we're interested. The process by which that aerosol interacts with the mechanics of the device under patient airflow is what generates this post-aerosolized formulation. And really, we're interested in trying to understand how the structure of the powders within that formulation are important in this context. So if we think of a typical DPI formulation, then we can see that usually the majority of formulations are composed of a carrier or a diluent. Specifically, it's really a diluent included as a bulking agent, but serves as a carrier aid. So we'll have a large particle size diluent. We'll typically have micronized API, although we could have spray-dried API present as well. And in addition to that, we usually have ternary agents, something, for example, like micronized lactose, or it could be magnesium stearate. Indeed, we could have 2 or 3 APIs present now, and of course, a second micronized API almost behaves like a ternary agent for the first API. So I'm going to look specifically at carrier-based formulations in this project, or in this presentation today. But of course, I'm aware that there are carrier-free products. There are now advanced engineered types of particle formulations as well. So really, we're going to look at how we can understand the structure and the performance of these typical DPI blends. So if we think about the critical material attributes then, and one of the key things that we're interested here is powder flow. And Gellert's analysis of 4 classes of powders, A, B, C, D, is really quite key here. And we can see, for example, the relationship between the particle size of the input material and the difference in density between the particle and the gas or the air phase. We're able to really define out a number of different behaviors. So in the typical size range of the carrier lactoses or the diluents, these are materials which have a particle size and density which are suitable for good flow. They fluidize relatively well. So they're going to be suitable for achieving good filling, good emptying under aerosolization forces. Whereas when we look at cohesive materials, these are materials with a much smaller particle size distribution. Well, we can see that these materials are very cohesive. The micronized materials, therefore, tend to have very poor flow and very poor fluidization. So really our goal in this aerosolization study and aerosolization processes are really to optimize the balance between these cohesive C-type powders and the aeratable A-type powders. And what we're really interested in understanding is how the addition of a C-type powder to the carrier lactose is going to change that powder flow. And we can see examples here of this, looking at the powder fluidization and emission from DPI formulations. What we can see here are 2 carrier grades of lactose, Respitose 003 and Lactohale 100. So these are large carrier size, large particle size carriers. And we can see the experimental videography here of looking at the emptying of these lactose powders. So there's an example at the start of the process, lactose powder at the start in an aerosolization blister model. And we can see that there's relatively good and efficient emptying of that large lactose powder from these. We get very good correlation between the CFD experimentation and the real life experimentation. So what we can see is that the emission and the fluidization of large particle diluents is efficient, it's consistent, and it's suitable for modeling. But when we move on to, this is with Lactohale 200. So this is a material that has a high proportion of fines caught up in the large carrier lactose as well. We can see that by adding these, with the addition of these small amounts of these class C powders into that large carrier lactose, that actually the emptying, the fluidization, and the aerosolization of that carrier lactose becomes very chaotic, it's very variable, and it's very difficult to model. So we can see the differences here between 3 different emptying profiles. And we see that here in these videos as well. There's very poor reproducibility of the emptying between video 1, video 2, video 3. So what we were trying to get to is to try and understand how this powder structural issue of adding class 3 powders into our class C powders into the carrier lactose changes the powder structure. And really, we're looking at approaches to investigating powder microstructure here. How do different aspects of particle size and shape affect the microstructure? How does particle size and shape interact to achieve a packing of the powder bed? How does the crystal form and crystallinity and variety of material attributes affect that microstructure? So really, microstructure is going to be a function of all of these different elements. And this is really where we're trying to use evolving analytical techniques to try and understand how microstructure is formed within the powder blends. So where we started from in this was the development of novel X-ray technologies, particularly from Zeiss, that were making it possible to look at materials on the size scale of inhalation formulations. We're all relatively familiar with X-ray technologies in pharmaceutical development, from looking at biological imaging using X-ray CT. Whereas X-ray physics, really up until relatively recently, hasn't been suitable for looking at materials of the size scale. We just simply didn't have the resolution. So if we look again here in this X-ray physics, where we're quite used to X-ray absorption, that's the technology that's used in making X-rays of broken bones, for example. We can see that there's an incident radiation beam of the X-ray. It enters the sample and it's attenuated on the exit. So material is absorbed by that sample. So we can see here that the exiting X-ray beams have a smaller amplitude, and it's this absorption which we're going to look at to try and identify the presence of the particulate phase in this gas particle mixture. So if we look at a typical powder here in 3 dimensions, we can see that there's a difference between the X-ray absorption of the particle phases versus the darker scale of the air. And if we look then at a magnification of a cross section of this, we can definitely see the differences between the particle phase here with the background air. So this is a typical X-ray absorption mode scan that's taken in 3 dimensions. It can be done in a variety of formats, for example, with the powder in a capsule or in capsule tubing, and we're even looking to see whether it can be done within blister type formats. So if you look at a typical image of this, here's the lactose 100 on the left of the screen, lactose 200 on the right of the screen, and we can clearly see now at least qualitative differences between these materials. We can see a higher proportion of fines in the lactose 200 than in the lactose 100, and we can see that even though this is a 2D cross slice, we can even see a 3-dimensional rendering. Let's go back to that. We can even see a 3-dimensional rendering of the particles in that mixture. So that's nice. It's great to be able to look qualitatively to try and see the powder structures, but is there any way that we can start to pull quantitative metrics to this? Well, we've because we're able to identify every single individual particle within that 3-dimensional matrix, we're able to measure out the volume of that individual particle, and from that, the volume of the particle, we're able to work out the diameters of the individual particles present. So in a non-destructive way, we're able to take these we're able to take images such as this in 3 dimensions. We're able to work out the volumes of the particles and therefore a volume size distribution, or a volume distribution of the particles, or a particle size distribution. And we can see these typical particle size distributions such as we're used to looking at from laser diffraction, and we can clearly see the difference between here the X-ray microscopy images of lactose 100 and the particle size distribution versus lactose 200. So if we look again at the qualitative level, we can see that it looks as if there's lots of fine particles in lactose 200 in comparison to lactose 100. And we can also see that in these particle size distributions. So here's the X-ray microscopy of lactose 100 in comparison to the X-ray microscopy of lactose 200. And although there's a slight difference between the X-ray measurements of lactose 100 here and the laser diffraction in red, we can see that we have good qualitative comparisons between the 2 different techniques. And of course, we need to remember that the laser diffraction is really a derived diameter based on a number of optical principles, whereas the particle size distribution from X-ray microscopy is calculated directly from the volume of each individual particle, not involving those assumptions of sphericity. So we're able to pull out particle size distributions, quantitative information, which is highly useful for us. So if we think then around the microstructure, so we've looked to see that we're able to pull out particle sizes and shapes. We're able to look at aspects of powder bed packing to see where those particles are located. The next step is really, can we start to look at functions of material attributes and crystal form and crystallinity on that microstructure? And this is where our colleagues and ourselves started to collaborate with Zeiss. So we'd like to thank everybody that's listed on this slide, but particularly this is work that was carried out in collaboration with our colleagues at Manchester, specifically Parmesh Kajar, who carried out a lot of the work with Joanna, the postdoc from Hertfordshire, and Rishi Bale from Zeiss, who also undertook a lot of the modelling work with us. And this really highlights some of the issues with pharmaceutical materials and X-ray microscopy. Pharmaceutical materials typically have quite low atomic weights with small differences in X-ray attenuation. And what we tried to do in this project was to look and see how we could use phase contrast, which I'll discuss in a moment, how phase contrast could be used to provide high contrast sensitivity for pharmaceutical materials. So this collaboration with Zeiss was really looking at emerging X-ray physics approaches, that's possible because of their new optical setups. And this optical setup particularly is using the properties of X-ray refraction and phase shift not just the absorption. So we can see the incident X-ray beam enters the sample, and due to refraction, there's an angle change of that refracted beam. So as the X-ray beam passes through, not only is it attenuated in its amplitude, but we also see a change in the phase angle. So that's this alpha here. So are we able to pick out any of these differences based on both refraction of the refraction angles of the X-ray beam, as well as the attenuation, to try and pick out subtle differences in the material properties? So if we just go back again, we can see this refraction of the beam. We can measure that angle of refraction, but we can also measure the amplitude differences of those individual waves. And it's really due to the high resolution detectors and the small pixel sizes on Zeiss's Versa instruments that we're able to pick out these subtle differences between materials that we're going to show on the next slide. And this is possible to do in both nanoscale X-ray microscopy, as well as microscale X-ray microscopy. And we can see here how these aspects show up. So we've got an individual particle here, and we've got the air. What we can see, because of the processes of refraction at the boundary of that particle there, we can see a bright fringe on the inside of the particle that's corresponding to this X-ray intensity here. And we've got a dark fringe on the outside of the particle due to this refraction behavior. So if we just take a quick flick back, we can see there's the angle change and the amplitude change, and we can see the consequences of that at this phase boundary between the particle and the air. So we're now able to identify very specifically the differences in the point of the perimeter of those particles. And in addition to that, different materials are going to have different intensities of these rings. So these fringes that occur around the particle are known as Fresnel images, or Fresnel fringes, and we're able to use that to pick out very fine detail of the material properties. So if we look at a typical example, the difference between an absorption mode, we can see here on the left, we can see, yes, it's possible to identify the particle, but when we move into the phase contrast mode, and this is on a nano-CT, we're able to pick out very, very fine details, very sharp edges of those particles. We're able to see the epoxy resin that we're using to mount the particle of lactohale onto our lactose monohydrate onto another particle here, and we're also able to see these interesting fractures that seem to run, voids that seem to run within the crystal itself. And of course, this isn't just a 2D technique. We can look in 3D, and we're able to see that all of these voids seem to, somewhat interestingly, align along in the same plane within that lactose. So this raises the question as to what these fringes really are and how they might impact on the particle itself. And that's something that we're looking at in closer detail with the material suppliers to try and understand whether it's a process-induced disorder. We don't think that it's related to the analytical technique itself, because we produce control crystalline lactoses that don't exhibit this behavior. So then we can also look down at the nanoscale of XRM. So here we have a single agglomerate of lactohale 300 that's mounted on top of a pin that we've scanned under the ultra instrument, the Nano-scale XRCT or XRM. And we can see the types of information that we're able to get out of this. So this is a typical 2D image of lactohale 300. We can see, yes, it's possible to see agglomeration, but really we're losing an awful lot of the fine detail that we see when we place this material inside a tube. So we can see the clustering of powders here. We can see a large agglomerate here within the tube. We can also see even larger agglomerates here. So really, what we're able to see here is a fine level of detail of particle organization that's just not present in the X-ray microscopy. So if we zoom in, we zoom in this region and we look at a specific agglomerate, we're able to see here, this is the agglomerate structure in a 3D, well, it's a 2.5D rendering image. We're able to work out particle size distributions within that agglomerate itself, and we're able to calculate out the porosity as being 72%. So this 72% porosity of that agglomerate might appear relatively high, but we can see that actually a vast majority of that is associated with air. And that's going to impact on the fluidization. So some of the other information that we can pull from this really is, now we're able to identify particle size distributions. Can we start to pull out particles of an individual size fraction, such as those lactohale agglomerates, and try and see where they're located in the blend? So we've taken our particle size distribution, we can, using the graphics, we can label up all of the particles that have a volume or particle size below about 10 to 20 microns and identify where they're distributed throughout the blend. So we can see in the lactohale 100, we're able to make a count of all of those particles in the volume that they occupy, and we can start to pull out and identify the location of each of these particles in the lactohale 200 that has many more fines. So we're able to identify very fine structures, porosity within agglomerates, locations of agglomerates within the powder blend, and we're able to understand material properties. So the next step is really, can we start to understand, now that we're able to map out material attributes, is it possible to identify where those materials are within the powder bed? And this is really the microstructural level that we're interested in. So here we can see two materials present. We can see the Fresnel fringes on the edges of these particles. We can see the Fresnel fringes on the edges of these particles to identify out those particles. And we can see slight differences in those phase contrasts. We can see some very bright white fringes here in comparison to some darker fringes. And we suspected that these are lactose in comparison to the lighter, smaller particles, which were the drug in this instance. So we have another way of really, with these Fresnel fringes and the differences in the phase contrast, we've got another kind of bow in the armory about being able to identify specific chemical differences between these materials in the powder blend. So that's what we can see here. We're able to label up all of the particles that have a different phase contrast behavior. We're identifying these in two colors here: yellow, which is the drug, or yellow, which is the lactose carrier, red, which is the drug, is terbutaline sulfate. And we're able to now build up a particle map of where those particles are distributed throughout the blend. So we're able to come up with ways of identifying really where different chemical phases are distributed throughout the blend. And this is quite an interesting way about being able to try and understand how we might have batch-to-batch variability and understand where exactly our API is located throughout the blend itself. So moving on to a more relevant study, where we've chosen just one of a range of studies I've been working at here, using lactohale as the carrier, fluticasone propionate at a relatively high concentration of 10% here, but it's an initial probe to try and understand and develop the methodology, using high shear mixing in the pico mixer, so trying to keep an industrially relevant process, and then trying to see if there's any way that we can identify this challenging material of a micronized material throughout a relevant pharmaceutical blend. This is a big challenge based on the small sizes of these particles. And what we can see is using the phase contrast and a patented post-process filter that Zeiss have developed, we're able to see really subtle differences between the lactose here, the large particles, but then also this gray scaling, which shows the presence of agglomerates coating those lactose crystals. So we're now able to identify where micronized drug phase is located with respect to the large carrier particles. And what we can see is that the FP is coating the outside of the lactose in different layers. And we're able to image that up here. We can see the large lactose carriers in purple, and we're able to identify where the drug is located. And not only that, we can also identify the density of the drug and the thickness of those drug coating layers. So if we take an individual particle such as this, we're able to identify that the drug seems to be located specifically on individual facets of the lactose carrier crystals. It's not distributed evenly on every single crystal face. And we're able to identify materials such as this, where we can identify in mixed agglomerates where we've got lactose, micronized lactose, or small particle size lactose combined with fluticasone propionate, and where that distributes over these complex clusters. So we're really able to build up microstructural information here of the FP distribution within that pharmaceutical blend. So we can also see now the position of the drug in, again, in 2.5D rendering. We can see where the drug is located, really occupying many of the spaces between the FP carrier particles, and in addition to that, coating the carrier surface. So really seeing how that micronized FP can act as a glue. And we can just see on this slide here the comparison between the typical 2D SEM types of information that we get around powder blend structure in comparison to these 3D structural techniques. So we really see a hell of a lot of detail in this 3D rendering, even if we can't identify out individual particles stuck to a lactose crystal. We're able to pull out structural information that could be used for comparative purposes. So what's still to come? Well, really that was method development in some ways. What's still to come from this? Well, we're looking at quantitative analysis of drug phase distribution. This is work that we're undertaking with AstraZeneca at the moment. We're also looking to see, can we identify the limits of detection for different chemical species in mixed blends? So how low are we able to detect in terms of drug content? We're looking at intra-particle structure for engineered spray-dried particles, and we're currently looking at how to index individual lactose crystal facets and how that might drive the particle adhesion. And with that, I'd just like to thank all of the researchers that were part of this collaboration, and sorry for running a little bit over time, but
Darragh, no problem. Very impressive, very impressive. Can I ask a question to begin, which is, this is new analytical capability. Is it a game changer? So what do you think will be the most exciting or revelatory new understandings that this might enable?
I think some of the most informative information is tautology. Some of the most informative aspects that we can get from this really are trying to identify how it is that the structure resists aerosolization. There's two things we can get. Can we identify differential distribution of the drug between the carrier for generic versus innovator products, or from batch to batch, to really have to cancel out the need to do repetitive kind of phase 1 validation studies and things like that. The second aspect is, can we use it mechanistically? We're at the point now where we're able to identify individual crystal particles and speciation between those particles based on X-ray diffraction tomography as well. So we'll be able to see which phases are responsible for the adhesion and cohesion of the powder blends. And they're the two real aspects. One is an analytical approach to try and understand batch-batch variability, and the other is mechanistic understanding.
Mm-hmm. So do you see it more as a development tool or quality control?
So I think really looking for the next couple of years, it's going to be used predominantly as a development tool, but using kind of AI-based approaches. I know Anders is going to talk, Anders Bro from Astra is going to talk about AI tomorrow morning, which I'm quite looking forward to. If we can build up significant libraries of powder images, we should be able to use it as a quality control tool, but it's building up a significant database of three-dimensional images that we can use for image comparison, a little bit like an automated number plate recognition system. Of course, it's difficult in 3D. That's probably where we need to get to for the QC approach.
Mm-hmm. And there's a technical question. What's the sensitivity of measurements to parameters like packing density, sample size, etc.?
Yeah, so our current sample size, we're able to look at around 10 milligram samples, which is a typical fill weight into a blister, which is what we're particularly interested in. We're currently looking down around the 0.5% weight content of drug. The particle size resolution that we can get is typically down to about roughly 2 microns on the microscale CT and down to about 200 nanometers on the nanoscale CT. The sizes of samples that we can use on nanoscale CT tend to be much smaller. We're down to around 1 milligram samples. But what we're really looking at doing is stitching between the two techniques. The nano CT will tell us the really nanoscale detail, and then we're able to transpose that up into the microscale for the larger sample sizes.
That's great, Darragh. We've got more questions coming in, but they're going to be a little bit too late for this session. We'll forward them on to you.
Yeah, and I can get back to that. I can see some of the people typing. I'll come back to that.
People are typing.
No problem. Thanks a million, Ben, and thanks to everybody for organising this. It's been a hard year for everybody. It's a great day yesterday, and hopefully today will be just as good.